Welcome to today's paper reading. Today's paper is titled, SEA-RAFT, Simple, Efficient, Accurate Raft for Optical Flow. This paper was published on AR14 by Yihan, Wang and colleagues from Princeton University. SEA-RAFT is a simplified, efficient, and accurate version of the RAFT model for optical flow. It introduces several key innovations, including the use of a mixture of Laplace loss for training, direct regression of an initial flow to accelerate convergence, and rigid motion pre-training to enhance generalization. These improvements result in state-of-the-art performance on the Spring benchmark, with a 3.69 endpoint-error (EP) and a 0.361 pixel outlier rate (1px), representing significant error reductions. Additionally, SEA-RAFT operates at least 2.3 times faster than existing methods while maintaining competitive accuracy. SEA-RAFT is a new variant of the RAFT architecture, designed to be both more efficient and more accurate in estimating optical flow. On the Spring benchmark, SEA-RAFT achieves a significant reduction in error, outperforming the next best method by 18% on the 1px outlier rate and 24% on endpoint error. Additionally, SEA-RAFT is at least 2.3 times faster than existing methods with comparable accuracy. The improvements in SEA-RAFT include the use of a mixture of Laplace loss, directly regressed initial flow, and rigid flow pre-training, which collectively enhance both the accuracy and efficiency of the model. Figure 1 presents the zero-shot performance of SEA-RAFT and other existing methods on the Spring training split. The latency is measured on an RTX 3090 with a batch size of 1 and an input resolution of 540 by 960. SEA-RAFT demonstrates an accuracy level close to the best achieved by MS-RAFT+, yet it is significantly more efficient. Specifically, SEA-RAFT is 11 times smaller in size and 24 times faster than MS-RAFT+. This performance highlights the efficiency and accuracy of SEA-RAFT in comparison to other state-of-the-art methods. In the field of optical flow estimation, classical approaches treated the problem as an optimization task aimed at maximizing visual similarity between corresponding pixels, often with strong regularization. Recent advancements, however, have shifted towards deep learning methods. For instance, FlowNets approached optical flow as a dense regression problem, utilizing stacked convolution blocks for prediction. More sophisticated models like DCNet and PWCNet introduced the concept of a 4D cost volume to explicitly model pixel correspondences. RAFT further enhanced this approach by combining multiscale 4D cost volumes with recurrent iterative refinements, leading to significant improvements. Our method introduces a new variant of RAFT with several key improvements, including a new loss function, direct regression of initial flow, rigid flow pre-training, and architectural simplifications. These enhancements are novel compared to existing RAFT variants, particularly our direct regression of initial flow, which significantly reduces the number of RAFT iterations needed. Figure 2 provides a visual summary of the key improvements introduced by SEA-RAFT over the original RAFT. These improvements include rigid flow pre-training, which enhances generalization despite limited flow diversity, a mixture of Laplace loss, which reduces overfitting to ambiguous cases, and direct regression of initial flow, which significantly reduces the number of iterations needed for refinement. These innovations collectively contribute to SEA-RAFT's superior efficiency and accuracy in optical flow estimation tasks. The iterative refinement process in RAFT involves two main components, feature and context encoders, and an RNN unit for refining predictions. This process builds a multiscale 4D correlation volume to compute similarities between feature maps. SEA-RAFT introduces significant improvements by reducing the number of iterations required for training and inference, using a mixture of Laplace loss to handle ambiguous cases, and directly regressing an initial flow estimate. Additionally, SEA-RAFT benefits from large-scale pre-training on tartan, which enhances generalization and includes simplifications to the original RAFT architecture for better efficiency and stability. Figure 3 illustrates the frequent occurrence of ambiguous cases in optical flow training data, primarily due to occlusion. These ambiguous cases can significantly impact the L1 loss, which is currently used by methods like RAFT 50, 56. The figure shows an error map highlighting these issues. To address this, our new training loss is designed to account for such uncertainties, thereby improving the model's performance in handling unpredictable flow situations. Figure 4 presents a visualization of the Spring test set, highlighting the application of a mixture of two Laplace distributions to handle both ordinary and ambiguous cases in optical flow estimation. The mixture is characterized by a mixing coefficient alpha, which ranges from 0 to 1, and a fixed beta-1 set to 0 to align with the L1 loss for ordinary cases. This approach allows the model to optimize for the L1 loss when possible, while also accounting for uncertainty in ambiguous cases, leading to improved accuracy in flow prediction. Figure 5 presents a visualization of optical flow results across three distinct datasets: Intel, KITTI, and Middlebury. The visualization highlights the application of the mixture of Laplace, mole, loss, which is designed to handle both ordinary and ambiguous cases in optical flow prediction. This approach involves a mixture of two Laplace distributions, with a mixing coefficient alpha, to better align with the endpoint-error metric and account for uncertainty. The figure demonstrates how this method improves accuracy and reduces the number of update iterations needed during inference, as detailed in the subsequent sections of the paper. The evaluation of SEA-RAFT is conducted on several datasets including Spring, KITTI, and Intel. Additionally, flying chairs, flying things, and HD1K are incorporated into the training pipeline. The effectiveness of tartan-air rigid flow pre-training is also verified. The SEA-RAFT model is implemented in PyTorch and comes in three variants: SEA-RAFT S, SEA-RAFT M, and SEA-RAFT L, differing in backbone choices and the number of iterations in inference. The training details include pre-training on tartan-air for 300K steps, followed by training on flying chairs and flying things 3D with specified batch sizes, input resolutions, and learning rates. Table 1 presents the performance of SEA-RAFT compared to existing methods on the Spring benchmark. The table highlights that even the smallest model, SEA-RAFT S, surpasses all other methods that do not use extra data. Specifically, SEA-RAFT S achieves superior results without fine-tuning on the Spring training set. Additionally, SEA-RAFT M demonstrates a significant margin of improvement on the Spring test set. The table also notes that all SEA-RAFT models undergo C++ T++ S++ K++ H training by default, which includes datasets like Intel, Flying Things 3D, KITTI, and HD1K. This comprehensive training approach contributes to the model's robust performance across various settings. Table 2 highlights SEA-RAFT's superior zero-shot performance on the KITTI training dataset. All methods are standardized with C++ training by default, with additional data noted in the first column. The symbols and asterisk operator indicate methods that use tiling during inference, and a 200K step ablation of GM flow, respectively. This table underscores SEA-RAFT's effectiveness in achieving top results without the need for extra data, showcasing the advantages of its mixture loss and architecture design. Table 3 highlights the superior speed of SEA-RAFT compared to other competitive methods in optical flow estimation. Specifically, SEA-RAFT is at least 1.8 times faster on the Intel test set and 4.6 times faster on the KITTI test set. This performance is achieved without compromising on accuracy, as all methods included in the comparison have undergone the same comprehensive training regimen, C++ T++ S++ K++ H, by default. The table also notes the use of extra data by each method and specifies that latency measurements were taken on an RTX 3090 with a batch size of 1 and an input resolution of 540 by 960. Additionally, it indicates that some methods employ a warm start strategy, denoted by star operator, and others use tiling-based test time optimizations, denoted by. This comprehensive comparison underscores SEA-RAFT's efficiency and effectiveness in real-world applications. Table 4 presents an ablation study focusing on the impact of pre-training, direct regression, RNN design, and loss designs on the Spring sub-AL dataset. Each row in the table represents a different configuration of these elements, allowing for a direct comparison with the baseline configuration shown in the first row. The study aims to identify how changes in these design choices affect the performance metrics, as detailed in Section 4.3 of the paper. Table 5 highlights the efficiency improvements of SEA-RAFT over RAFT in terms of iterative refinement costs. It demonstrates that SEA-RAFT not only significantly reduces these costs, but also enables the use of larger backbones without compromising speed. The table uses K and S to represent RAFT's performance on the KITTI and Spring datasets, respectively, showing that SEA-RAFT maintains or improves upon these benchmarks while being more cost-effective. Figure 6 illustrates the impact of increasing iterations on the variance within a mixture of Laplace model. The data clearly shows that as the number of iterations increases, the variance decreases, signifying that the model becomes more confident with each additional iteration. This trend underscores the importance of iterative refinement in enhancing the reliability and accuracy of the model's predictions. Figure 7 illustrates the relationship between latency and the number of iterations in optical flow estimation. The graph clearly shows that as the number of iterations increases, the latency also increases almost linearly. This observation is crucial for understanding the computational efficiency of different optical flow estimation methods. Specifically, SEA-RAFT, a variant of RAFT, significantly reduces the cost of iterative refinements, which allows for the use of larger backbones without increasing computational costs. This makes SEA-RAFT more hardware-friendly and efficient, enabling it to achieve high accuracy across various datasets while maintaining strong cross-dataset generalization and state-of-the-art accuracy-speed trade-offs. SEA-RAFT, a variant of RAFT, demonstrates high accuracy across various datasets, strong cross-dataset generalization, and state-of-the-art accuracy-speed trade-offs. This makes it highly applicable for real-world high-resolution optical flow tasks. The work was partially supported by the National Science Foundation, and contributions from all parties involved are acknowledged for their impact on the research. Thank you for watching.